Welcome to the class of stochastic processes, convolutions of exponential random variables. Convolution is a technique that allows us to derive the distribution of summation xi when each xi distribution has been known. For example, if xi is independent exponential random variable with parameter lambda I, then summation xi is called hypo-exponential random variable. And then when n is equal to 2, we can derive the density function of x1 plus x2, which can be written as integration fx1s fx2 t minus s, and then we take integration from 0 to t ds. And because x1 and x2 are both exponential random variables, so we can write their density function like this: lambda 1 e to the minus lambda 1 s, and lambda 2 e to the minus lambda 2 t minus s. And we can bring lambda 1, lambda 2 e to the negative lambda 2 t out of the integration like this. And after some algebra, we can derive the density function of x1 plus x2, which will be like this. Similarly, we can derive the density function of x1 minus x2 minus x3, and the result will be like this. And we can further generalize this concept and derive the density function of x1 plus x2 plus x3 up to plus xn, and the result will be like this. And if we have known the density function of summation xi, we can also derive the distribution function of summation xi. And if we know the distribution function of summation xi, we know the probability of summation xi is greater than t, and the result will be like this. Proposition: Tn n is equal to 1, 2, 3 are independent, identically distributed exponential random variables having mean 1 over lambda. Now we consider Sn, which is defined as summation Ti. So Sn is called waiting time until nth event, and Ti here is called inter-arrival time. So we can derive the distribution function of Sn. So f of Snt by definition will be equal to probability of Sn is less than or equal to t. And because Sn represents the waiting time until the nth event, so if Sn is less than t, that simply means Nt is greater than or equal to n, because the waiting time until the nth event is less than or equal to t. That means that by time t, we will have more than n events. So this event, Sn is less than or equal to t, will simply be equal to Nt is greater than or equal to n. So their probability will be equal to each other. And the probability of Nt is greater than or equal to n, because Nt is Poisson random variables, right? So Nt is greater than or equal to n. This probability will be equal to summation e to the lambda t times lambda t, e to the minus lambda t times lambda t to the power of j divided by j factorial. And then we take summation from n to infinity because n of t is greater than or equal to n. So with this distribution function, we can derive the density function. And by deriving the distribution function with respect to t, so dfSnt dt, and the result will be lambda to the power of n, t to the power of n minus 1, e to the minus lambda t, and divided by gamma n. So based on this result, we know that Sn is a gamma random variable with parameter n and lambda. Counting process. NT is said to be a counting process if NT represents the total number of events that occur by time t. So for example, NT can represent the number of persons who enter a bank at or prior to time t. So for example, if this is time 0 and this is time t, and counting process simply means the number of events that happen before time t. So in this example, we have 4 occurrences. So n of t will be 4. N of t will be 4 in this example. So n of t, we ask n of t to satisfy. Number 1, n of t is greater than or equal to 0 because n of t means the number of events, right? So naturally, n of t will be greater than or equal to 0. Number 2, n of t is integer valued. This goes without saying because that n of t represents the total number of events. 3, if s less than t, then n of s will be less than or equal to n of t. Because if you have longer period of time, you will have more occurrences of events. That's very natural. 4, for s less than t, nt minus ns equals the number of events that occurs between s and t. Poisson process. Poisson process is actually a very special case of the counting process previously described. And in particular, Poisson process is required to satisfy 2 assumptions. Number 1, independent increment. What does that mean? Independent increment means the number of events in S1t, this time period, is independent of the number of events in the time period S2 T2. So S1 T1 and S2 T2 do not overlap. So for two unoverlapped period of times, the number of events happen within that period of time does not affect each other. So that means they are independent of each other. This is called independent increments. Stationary increments. Stationary increment means the distribution of the number of events that occur in any interval of time depends only on the length of the time interval. So for example, if the Poisson process represents the number of buses that come like in an hour, then this stationary increment means even if this period of time is from 8 a.m. to 9 a.m. or 9 a.m. to 10 a.m. The number of buses follow the same distribution. So that does not depend on 8 a.m. or 9 a.m. That only depends on the length of the period of time. And all of them are 1 hour, right? So just remember, stationary increment means the number of events that occur in any interval of time depends only on the length, but not the time point itself. We put one remark here. One of the most important counting process is the Poisson process. Definition of the Poisson process. So the counting process NT is said to be Poisson process having rate lambda. Lambda is greater than 0 if the following 3 conditions are satisfied. 1. N of 0 is equal to 0, so meaning the system starts from 0. 2. The process has independent increment. We have known that. 3. For S and T greater than or equal to 0, the probability of n s plus t minus n of s is equal to n will be equal to e to the minus lambda t to the power of n. I'm sorry, this is a typo. Divided by n factorial. So that means this number of events happen between s and s plus t will be a Poisson random variable. So we have a note here. N of s plus t minus n of s is equal to n is the number of events in any length t. Remark. So from 3, we know Poisson process has stationary increment, because if you look at this probability mass function, you can see that this probability mass function PMF has nothing to do with S, right? Because this time is from S to S plus T. And we say that the number of events that occur within this period is only dependent upon the length of this time period, which is T, and has nothing to do with S. And if you look at this PMF, you can see that this PMF has no S in there, right? So that simply implies that this is actually stationary. So we have a remark here. Poisson process has stationary increments, and we know that expectation of n of t will be lambda t, where lambda is the rate of the process. Theorem. In previous class, actually, I have mentioned that the binomial distribution and the Poisson process has very strong relationship, simply because the Poisson process in essence is actually binomial distribution. It's binomial. So, and we have a theorem here. So if x is a random variable that follows binomial distribution NP, when n goes to infinity, so that means if you have a period of time, you can chop this period of time in many small intervals. So when n goes to infinity, p goes to 0. That means the probability that each very small time interval that the event will happen will be very small. And the np is equal to lambda. Then in this case, x, this random variable x, will be Poisson random variable with lambda equal to np. Now, we prove this. Because x is binomial random variable, so we know that the PMF of x will be c n choose x, p to the x, 1 minus p to the n minus x. Now, because np is equal to lambda, so p is equal to lambda over n. So we can plug lambda over n here. So we have c n choose x, lambda over n to the power of x times 1 minus lambda over n minus x. Then cn choose x can be written as n factorial divided by x factorial, n minus x factorial, right? And also 1 minus lambda over n to the power of n minus x can be written, can be separated as 1 minus lambda over n to the power of minus x times 1 minus lambda over n to the power of n. And then this c choose x, this factorial expression can be written as this, right? Because basically this n factorial and n minus x factorial has some terms to be cancelled out, and we are left with this. And also, if we keep going, then we know that actually this we can swap the x factorial and the n to the power of x. So we can swap these two. So this is n power of x. So we have x terms in the denominator. And in the numerator, we also have x terms. Okay? And here we have lambda to the power of x divided by x factorial because we have swapped their order, right? And the rest of the equation does not change. Okay? So now we let n goes to infinity. Then obviously this is n over n, n minus 1 over n, and we keep going. And when n goes to infinity, all of them are equal to 1. So this whole term is equal to 1. So we are left with this. Lambda to the power of x divided by x factorial times 1 minus lambda over n to the power of minus x, and times 1 minus lambda over n to the power of n. And then, because we know that based on the calculus knowledge, we have known that limit 1 minus lambda over n to the power of n would be equal to e to the power of minus lambda. So basically, this, when n goes to infinity, this will be e to the power of minus lambda. And when n goes to infinity, this will be 1. Because lambda over n, when n goes to infinity, this will be 0, right? So we are left with 1 to the power of minus x, which will be 1, right? So it turns out that we have lambda to the power of x divided by x factorial times e to the minus lambda. And what is that? That is exactly the PMF of Poisson random variable, right? So we know that x is Poisson random variable with parameter lambda here. So we simply prove that when x is binomial random variable, and when n goes to infinity, p goes to 0, np is equal to lambda, then this random variable x will be Poisson random variable with parameter lambda being equal to np. We want to introduce definition here. The definition f of something is said to be little o of h if this definition if limit h goes to 0, f of h divided by h is equal to 0. And that means when h goes to 0, this function f of h is even smaller, that converts to 0 even faster than h. So the limit h goes to 0 of the f of h divided by h will be 0, right? I give you two examples here. So f of x is equal to x squared. This is little o of x because h squared, you put h to the function x squared, right? So h squared divided by h. And this is h. Limit h goes to 0 of h is 0, right? So that satisfies this definition. So we say x squared is little o of x. But f of x is equal to x. This is not little o of x because limit h to go to 0, h over h is equal to 1, not 0, right? So this is not little o of x. So when you say a function is of little o of x, that simply means that converts to 0 faster than x, okay? Another way to define Poisson process. Poisson process can also be defined as counting process n of t having rate lambda. If number 1, similarly, the system starts from 0. Number 2, the process is stationary in the independent increment. And number 3, probability of nf of h is equal to 1. This probability is equal to lambda h. See, this probability is only dependent on the length of the time period, which is h, plus little o of h. Little o of h, you can view it as 0 because in the previous slide, we have known that little o of h simply means when h is very small. Little o of h is even smaller, much smaller, right? When h is very close to 0. So you can view it as 0, basically. Okay? So that simply means the probability of nh is equal to 1 is equal to lambda h. So that means this probability is proportional to the time period h, the length of the time period h. Also, probability of nh is greater than or equal to 2 will be little o of h. So that is basically 0. So that means when h which means the length of time period is very small, then basically there will be no possibility that you have two occurrences of events. Inter-arrival and waiting time distribution. Consider a Poisson process, and we let Tn denote the sequence of inter-arrival times. So Tn are called inter-arrival times. Now we want to derive the distribution of Tn. Now, the event that T1 is greater than T if and only if that no event of the Poisson process occur between 0 and T, right? Because T1 means the first event, right? And the inter-arrival time, okay, T1 here, the first event, the first arrival between 0 and T, that means no event will happen between 0 and T, right? Because T1 means the first event, first arrival, right? So probability of T1 greater than T, because T1 greater than T, this event simply means NT is equal to 0, right? And we know that NT, if T1, if this is the Poisson process, and T1 is greater than T, then NT is the Poisson random variable. And NT is equal to 0, this probability will be e to the minus lambda t to the power of 0 divided by 0 factorial, which is e to the power of minus lambda t. So based on this result, we know that we can recognize that T1 is actually an exponential random variable with mean 1 over lambda. Now we consider T2. Probability of T2 greater than T can be written as probability of T2 greater than T conditional on T1, and then we take expectation with respect to T1. Now we look at the expectation inside. So probability of T2 greater than T conditional on T1 is S. So that means from S to S plus T, there will be no event because T2 is greater than T, right? So that means if this is S and this is S plus T and T2, so the inter-arrival time T2 is greater than T, so T2, so the second arrival will happen here. So between S and S plus T, there will be no event, right? So 0 event in S and S plus T. Conditional on T1 is equal to F. With or without this condition, it does not matter at all because we said this is Poisson process is stationary, and that means this distribution has nothing to do with S. Remember that, right? So we can simply ignore this condition. Okay? So 0 event in S and S plus T, this probability will be e to the minus lambda t. Okay? So this because this is stationary. So T2 is exponential random variable with mean 1 over lambda, simply like T1, right? So we know that if this is a Poisson process, T1, T2, T3, T4, all the inter-arrival times will be exponential random variables with the same parameter lambda, or mean 1 over lambda. Proposition. Tn are independent, identically distributed exponential random variables having mean 1 over lambda. That simply summarize our conclusion previously. Now we look at the waiting time distribution. So let Sn be the arrival time of the nth event, also called the waiting time until the nth event. So Sn will be the waiting time. So for example, this is time 0, and this is the first arrival, this is second arrival, third arrival, fourth arrival. So this is T1, and this is T2, this is T3, and this is T4. And then the whole period of time is called S4. So S4 is the waiting time until the fourth arrival in this example. Okay? So, and we know that if Ti, all the Tis are exponential random variables, and based on the convolution technique, we can derive that S4 or Sn has a gamma distribution with parameter n and lambda. Example, suppose that people immigrate into a territory at a Poisson rate lambda is equal to 1 per day. We have two questions here. First, what is the expected time until the 10th immigrant arrives? Second, what is the probability that the elapsed time between the 10th and 11th arrival exceeds 2 days? So basically, the first question is asking for expectation of S10. And we know that because if this is a Poisson process, then we know that the inter-arrival time will be exponential. So S10, this random variable will be gamma, right? So expectation of S10, we know that if gamma, S is a gamma random variable, then expectation of S will be alpha over lambda. So now because this is the 10th, we are looking at the 10th immigrant, right? So alpha will be 10. So 10 over lambda. So lambda is 1, right? So 10 over lambda will be 10 days. The second question, the probability that the elapsed time, so mean the period of time between the 10th and the 11th arrival. So we are looking at the T11 greater than 2. So probability of T11 greater than 2 will be equal to e to the minus lambda T, right? So T is 2, so minus 2 lambda. And because lambda is equal to 1, right? So that is e to the minus 2, which will be 0.133. Some further properties of Poisson processes. If we consider a Poisson process NT, then this Poisson process NT, comes in with the rate lambda. And suppose for each arrival, then every arrival can be divided into two classes, type 1 or type 2, with P, probability P or probability 1 minus P. Then N1 is called the number of type 1, N2 is called the number of type 2, then NT is N1 plus N2. And then we have this very important proposition. That means N1 and N2 are both Poisson processes having rate lambda P and lambda 1 minus P. And also, these two processes are independent. So for example, you can think of the arrival like some manufacturing process, and some products are manufactured. So if this is time 0, okay, and this is the first arrival, second arrival, third arrival, fourth arrival, fifth, sixth arrival. Okay, so if this arrival, so if every product can be classified as defective or non-defective. Okay, so for example, if this check means defective, then so every time we have probability P, so this comes in with rate lambda, and every product can be classified of defective product with probability P, okay, and then non-defective with probability 1 minus P. Then this proposition simply says that this check, that means defective products, that is still a Poisson process with parameter lambda P. And this, that is non-defective, right? So I use circle to represent the non-defective. And this circle process is also a Poisson process with parameter lambda times 1 minus p. And also these two processes are independent to each other. So basically, for a grand Poisson process, you can divide that into two sub-Poisson processes with lambda parameters, lambda p, and lambda times 1 minus p. Example, suppose non-negative offers to buy an item that you want to sell arrive according to a Poisson process with rate lambda. Assume that each offer is the value of a continuous random variable having density function f of x. And once the offer is presented to you, you must either accept it or reject it and wait for the next offer. And we suppose that you incur costs at a rate C per unit time until the item is sold, and that your objective is to maximize the expected total return, which is the total return, which is the amount received minus the total cost. Remember, we have some cost incurred if you are waiting, right? We have some cost C incurred per time when you are waiting. So you want to employ a policy that accepts the first offer that is greater than some specified value y. So you have to decide on the value of y. And so we call this a y policy. And now we want to decide on the value of y. So basically, you have some item at hand, and then some people will present offers to you, and the offers present to you follows the Poisson process with rate lambda. And now you have every time you see an offer, you have to decide whether you accept it or reject it. If you decide to wait, then probably later you are going to see a better offer, but that's still at some cost, right? Because when you are waiting, it incurs some waiting costs here. So you kind of want to decide on the optimal value of y. So think about that. If you put y as a very large value, then that means you only accept a very, very good offer. Then you may wait for a long time. Then ultimately, this may not be a very good policy, right? But on the other hand, if y is very small, then basically you accept every offer that is presented to you, then maybe that's not a very good deal either. So if we want to mathematically solve the problem, how can we do that? So first we look at the distribution function of x. So f of x, by definition, this is the probability of x is less than or equal to little x, right? Okay, so f bar of x will be probability of x greater than x. So by definition, that is f of u du, and we take integration from x to infinity. Now, with this notation, the probability of offer greater than y can be written as the probability of offer greater than y can be written as probability of x greater than y, and that can be expressed as f bar of y. Now, because the arrival is according to a Poisson process with rate lambda, so the accepted offer occur is also according to a Poisson process. Remember the proposition we just learned, right? This Poisson process each arrival can be classified as accepted offer or rejected offer. So if this is accepted, and then the probability will be f bar of y, right? And we say this sub-Poisson process will be having the rate lambda f bar of y. That is the proposition we just learned, right? Now we look at the return. So the expectation of the return can be written as expectation of the amount of the accepted offer minus the cost, the waiting time cost, right? And that is C times the waiting time, or called time to accept. So the expectation of the amount of accepted offer can be written as expectation of X given X is greater than Y, right? Because you employ Y policy, you only accept the offer only when X is greater than Y, right? So when X is greater than Y, we want to calculate the amount of the offer accepted. So that is expectation of X. Minus C times time to accept. And because the accepted offer is also a Poisson process with rate lambda f bar of Y. So the expectation of time to accept will be 1 over lambda f bar of Y. Now, we write expectation of X given X greater than Y as Y take integration Y to infinity X times f of X divided by f bar of Y dy and times minus C over lambda f bar of Y. So after some organization work, and it will be like this. Now we want to derive the best value of Y, right? So we take derivative with respect to Y and make it equal to 0. And recall that this expectation involves some integration here, and now you want to take derivative. So we have to apply so-called Leibniz Formula. Okay, so if you apply this formula, you can find that this equation will be like this. Okay, so if we organize this equation, it turns out that we will see that Y times f bar of Y will be equal to X f of X dx and the integration from Y to infinity minus C over lambda. Or if we keep going, it turns out that we will have this equation like this, meaning the Y, the optimal Y value should satisfy X minus Y f of X dx, and we take integration from Y to infinity, and that should be equal to C over lambda. Okay, now think about this. The left hand side can be viewed as X minus Y plus, right? X minus Y plus simply means this X minus Y only has positive values, when X minus Y is greater than or equal to 0, right? And that is the definition here, because we take integration from Y to infinity. So X minus Y is always positive, right? So, and we know that this integration is actually the expectation, right? So basically the left hand side is the expectation of X minus Y plus. And expectation of X minus Y plus is actually this curve. This is the decreasing function. So when Y increases, this function decreases. Why is that? Because when Y increases, X minus Y tend to be less positive, right? So that this function decreases. And C over lambda can be this true red line here, the straight line here. So when C over lambda is this line, then this is the optimal Y policy. But if C over lambda is this red line here, meaning when lambda is very small, then C over lambda is very large, right? And in this case, the Y star will be here. So Y star will be 0. That means you accept any offer that is presented to you. Okay? So our conclusion will be like this. When the expectation of X means when Y is equal to 0, so that is this point. This point is expectation of X. So that when expectation of X is less than C over lambda, then we say Y star would be 0, right? Y star would be 0, so that you accept any offer. So that shows no matter what the offer is, it is not worth waiting. You just take it. Okay? But when expectation of X is greater than or equal to C over lambda, then Y will be optimal only if this curve expectation of x minus y plus intercept the straight line C over lambda. So that means this point. Okay? Another example called the coupon collecting problem. Suppose that there are n different types of coupons, and each time a person collects a coupon, it is independently of ones previously obtained. A type J coupon with probability Pj and summation Pj is 1. Let n be the number of coupons one needs to collect in order to have a complete collection. So that means you have to collect all the n different types of coupons, at least one of each type. Now we want to find the expectation of n. So that means n is actually a random variable, right? Because the number of coupons you need to collect to have a complete set can be very different from time to time, right? So we look at the solution here. Let nj be the number of coupons one must collect to obtain j coupon. Okay? So basically, so for example, if we have, so if m is 3, okay? So we have the first coupon, second coupon, the third coupon here. So for example, if the first coupon takes like 2 coupons to collect to get the first coupon, and the second type coupon takes like 3, and the third coupon takes 1. So we at least need to have 3 coupons, right, to get all the 3 types, right? So basically, the n will be maximum of nj, right? The maximum of nj to collect all the different type of coupons. But then this representation, as you may have noticed, that this representation is not useful because nj is not independent, right? So these 2 coupons may overlap with these 3 coupons, may overlap with this 1 coupon. So you can, even if you can write n as the maximum nj, this is not useful, right? Because this nj is not independent, right? So this solution is not useful. Now we look at this solution, another solution here. If we consider a Poisson process with rate lambda being equal to 1, suppose that coupons are collected at times chosen according to a Poisson process with lambda equal to 1. Then, based on the previous proposition, you know that lambda is equal to 1. When that Poisson process comes in, you can divide this grand Poisson process into m sub-Poisson process with rate lambda times p1. And because lambda is equal to 1, so that is p1, and lambda p2, and so that is p2 up to pm. Right? Now, suppose, and why we want to do that? Because remember, these all sub-Poisson process are proved to be independent Poisson process. Okay? So that means if I let njt denote the number of type j coupons collected by time t, then we have one very, very important advantage here. That is, nj of t are independent Poisson process, and lambda pj will be pj because lambda is equal to 1. And this independent will give us some very important advantage for solving the problem. We'll see that very soon. Now, I let xj be the time of the first event of the jth process. So the time that I have a complete set of the coupons is called x. And that is obviously the maximum of xj, j from 1 to n. So x denotes the time at which a complete collection is collected, right? So, and know that xj are independent exponential random variable with rate Pj because we know that the sub-Poisson processes are independent to each other, right? So the xj are independent exponential random variables. Now, the probability of x less than t will be, because x means the maximum xj, right? So the maximum xj less than t. And maximum xj less than t means every xj is less than t for all j from 1 to n. And we know that xj is exponential random variable, right? So that is, the probability will be 1 minus e to the lambda. Lambda is pj, right? T. So minus pjt. And because these xj are independent exponential, right? So I can put a multiplication here. Now, the expectation of x can be written as probability by definition, that is probability x greater than t. Then we take integration from 0 to infinity, right? So probability of x greater than t, that is 1 minus the whole thing, right? So that is 1 minus this, okay? Now, we want to relate, because expectation of x means the expectation of the time that it takes to collect all m types of coupons, right? But actually, what we are really interested is expectation of n. That means the expectation of the number of coupons it takes to collect a complete set of the coupons, right? So we can relate. We want to relate expectation of x to expectation of n. Remember, let me emphasize this again. So n is the number of coupons it takes, and x, on the other hand, represent the time until one has a complete set. So n is the number of coupons that is discrete, right? X is continuous because that represents time, okay? But we know that x and n may have a relationship. What is that? Because we know x, this is represent time, is equal to summation ti, because x can represent the waiting time, right? So ti is the ith inter-arrival time from 1 to n. N represent the number of coupons it takes to get a complete set, okay? And we know that ti is a exponential random variable with parameter 1, right? And n is independent of ti. So expectation of x given capital N is equal to n. That is expectation of summation ti given n is equal to n. So when n is equal to n, we can simply replace this n by little n, right? So expectation of summation ti, I from 1 to n, would be equal to n times expectation of ti, okay? So if we know that when capital N is equal to little n, this expectation is like this. Then if we go back to look at capital N, which is a random variable, we know that this is, based on this, we know that this is capital N times expectation of ti. But we know that expectation of ti is equal to 1 because ti is an exponential random variable, right? So this expectation of ti is equal to 1. So n times 1, so we have 1 here. Okay? So now, expectation of s given n, we know that this is n, right? So basically, but we know that expectation of s given n is equal to expectation of x. But this is n, so this is expectation of n, right? Okay? Okay, so expectation of n is actually equal to expectation of x. Okay? And then, what is the expectation of x? Okay, expectation of x is here. And we have known that, right? So that is here. So basically, we have solved that the expectation of x is here, is like this. And that is exactly the expectation of n. So the number of coupons that it takes to collect all the m types of coupons will can be written as this.